Right, so in this video I'm going to have a look at the Leaving Certificate Higher Level Maths Paper 1 for 2018, and I'm going to have a look at question 4. So first part of this question involves proving the Moivre's theorem effectively. So it's we got to prove that cos theta plus I sine theta all to the power of n is equal to cos n theta plus I sine n theta, where I squared is equal to -1. So basically it just means that you can take this n here, the power here, bring it down, multiply it by the angle here. So bring it down in front of the angle. Okay, so we got to use induction to prove this. So let's start. So we're going to first of all look at, just to see, is the proposition true for, is this true for n is equal to 1? So we got to just prove this for positive integers, so natural numbers in other words. So first thing we're going to do is look at, is the proposition true for n is equal to 1? So let's look at the left hand side first. So the left hand side here is just this part here. So in other words, cos theta plus I sine theta all to the power of 1 will give us just simply cos theta plus I sine theta. Now the right hand side then, on the other hand, the right hand side is this part here. So we've got cos n theta, in other words 1 theta, plus I sine 1 theta. That's just going to be equal to, again, cos theta plus I sine theta. So the left hand side is equal to the right hand side, therefore it's true for n is equal to 1. Okay, so that's just step 1 if you like. So step 2 then is to prove that it's true for n is equal to k plus 1, given that it's true for n is equal to k. So we're going to assume the proposition is true for n is equal to some value called k. So we're going to assume that it is true for n is equal to k. We've got to prove that it is true for n is equal to k plus 1. Right, so we'll just write down what we're given. So what we're going to be given here, that it's true for n is equal to k. So we're going to assume that, in other words, cos theta plus I sine theta all to the power of k is in fact equal to cos k theta plus I sine k theta. So we're going to assume that this is true. So what we want to prove then, here is that cos theta plus I sine theta to the power of k plus 1 is equal to cos k plus 1 theta plus I sine k plus 1 theta. So here we're assuming that this is true. So in other words, that cos theta plus I sine theta to the power of some number k is equal to cos k theta plus I sine k theta. We can bring the k down here, and it does work. It is actually true. We're assuming that's true. We got to prove that it's true for k plus 1. So when the power is k plus 1, can we bring the k plus 1 down here? Now what we're going to do here is just look at the left hand side of this equation here. So we want to prove this. So I'm just going to look at this part here. We're just going to look at this part here and we're going to see if we can turn that into the right hand side. So we're just going to look at the left hand side here. Whoops. The left hand side here. So the left hand side is cos theta plus I sine theta to the power of k plus 1. We're going to look at that and see, can we turn it into this here. So if you look at this left hand side here, we can actually break this up using the laws of indices here. We can break this up into cos theta plus I sine theta to the power of k multiplied by cos theta plus I sine theta. So all I'm doing here is saying something like x to the power of k plus 1. That's just equal to x to the power of k times x to the power of 1. So k, you add the powers here. X to the power of k times x to the power of k, x to the power of k times x to the power of 1 is just equal to x to the power of k plus 1. I'm just adding the powers here. Same here, this to the power of k times this to the power of 1 is equal to this to the power of k plus 1, adding the powers. Now, we know that this part here works. This is true. We're given that. We're assuming that cos theta plus I sine theta to the power of k is equal to cos k theta plus I sine k theta. So I can bring the k down here. We've assumed that that is true. So I'm just going to write that out next. So that's going to be equal to cos k theta plus I sine k theta. So that's this bit here, multiplied by cos theta plus I sine theta. Next thing I'm going to do is just multiply all of this out. So I'm going to multiply this by this, this by this, this by this, and this by this. So what do we end up with? Well, we end up with cos k theta multiplied by cos theta, that's this times this, multiply this one by this term here, so that's plus cos k theta times I sine theta. These are multiplied here. Cos k theta times I sine theta. Now I'm going to multiply these two, so this is plus I sine k theta, that's this bit here, multiplied by cos theta. And finally I'm going to multiply these two terms here. So this is plus I times I is I squared, and we're left with sine k theta sine theta. Okay, next thing I'm going to do is I'm going to put the real parts together and I'm going to put the imaginary parts together. Now the real parts are this one here, and in fact this one here. Even though it has an I in here, this I squared here is minus 1. So this is actually, this part here will just turn into minus sine k theta sine theta. These two parts here then are going to be the imaginary parts. I'm going to take these two parts here, put them together, and factorize out the I. So let's do that. So the first part here is, we'll put it in brackets here, cos k theta cos theta. This part here then is just going to be minus 1 times sine k theta sine theta. And here then we end up with plus, I'm factorizing out the I here as well. There's an I here and an I here. So we end up with cos k theta sine theta. That's this one. And here we end up with sine k theta cos theta. Okay, so really what we've got here is real plus imaginary. Now, if you look at this part here, what we've actually ended up with here is cos A cos B minus sine A sine B. And from your tables you should realize, or you should see, that that's just equal to cos A plus B. So I mean really we've got this part here is just your A, this is the theta is the B, this is A here, this is B. So from your tables you should see that this, as I say, is just equal to cos A plus B. So all of this just turns into cos K theta, which is our A, plus theta, which is our B. Similarly on this side here we have cos A, we'll just call this one A, this is B, so this is A, this is B. So you can see from your tables as well that this is really just sine A plus B, sine A plus B. So really this just turns into sine, this just turns into sine K theta. Just put a big bracket around here. This is sine K theta plus theta. Okay, so finally then, or almost finally anyway, we can just factorize out the theta here. So we end up with cos K plus 1 theta. All I've done is taken the theta outside the bracket here. Similarly here we've got I sine K plus 1 theta. And that is the right hand side up here. We had to prove that we started with this here on the left hand side, and we did a lot of algebra down along here, and we did in fact end up with the right hand side. So this is true. So if we assume that the proposition is true for K, so in other words cos theta plus I sine theta to the power of K is equal to cos K theta plus I sine theta, then it will be true for K plus 1. Now we've already shown that the proposition is true for n is equal to 1. It does work for 1. So if it works for 1, then by what we've just done here, it's true for K plus 1, in other words 1 plus 1, which is 2. So if the proposition is true for 1, it's true for 2. If it's true for 2, it'll be true for 2 plus 1, which is 3. If it's true for 3, it'll be true for 4, and so on and so on and so on. So what we can say then is, I'll just write it out here, I'll just move this down a little bit. This is part B of the question. Just get this out of the way here. Now what we can say here then is, this is really the last step here, step 3 I think it is. We can say that assuming the proposition is true for K, then it is true for n is equal to K plus 1. Therefore, by induction, the proposition is true for all natural numbers. All n is an element of n. Okay, and that's it. That's really the Moivre's theorem there, if you like. So let's look at the second part of this question here. This is using the Moivre's theorem here. We've got to raise this complex number to the power of 3. So what we've got to do first really is convert this into polar form and then use the Moivre's theorem to work it out. So let's take this complex number here in the brackets. It's minus 1 over 2 plus root 3 over 2i. Now let's just have a look at that. Where would that be on our complex plane? Well, it's going to be up here somewhere. So because we're going out the left hand side here, this is our real number line, this is our imaginary number line here. So we're going out here minus a half, and then up here, so out to here is minus a half, and then we're going up along here root 3 over 2i. So what we've got to do for this is two things. To convert this into polar form, we've got to find this angle here. So we've got to work out what this angle here is. We'll call it theta. And we've also got to work out what this length is here. We'll call that r. So we've got to work out the modulus of this complex number, which is r. We've got to work out the argument, which is theta. So in order to work out the argument here, what we're going to do first of all is work out what this angle here is. It's reference angle, if you like, this alpha here. So let's do that first. So we have a triangle here. It's going to look like this. We have our alpha in here. We know that the absolute distance out here is a half, and the absolute distance here is √3/2. So I'm just going to use tan. We're going to use tan here. So I'm going to say the tan of this angle alpha is equal to √3/2 all over a half, opposite over adjacent. If you work that out, you just simply get √3. So the tan of alpha here, so in other words, I flipped this half upside down and multiplied, and the 2's cancelled. I ended up with √3. So tan of alpha is √3, and the tan inverse of √3, then you can look this up. This is one of your special angles, if you like. So you can look this up in your table, in your maths tables, but you'll find that it's pi/3. So alpha will be pi/3. So this angle here will be pi/3. So if this angle here excuse me, is pi/3, this angle out to here is pi, which is really just, if you like, 3 pi/3. So we're going back. This angle here is pi/3, so we're going back 1. So that will give us theta here is equal to 2 pi/3. So we'll just say here theta then is going to be 2 pi/3. So now we know the argument of the polar form of this complex number. So 2 pi/3 is going to be our theta. Now we've got to also work out this length here, this distance here, which is really just Pythagoras' theorem, but we're going to work out r here, which is really the square root of a squared plus b squared. And the a is this number here, and the b is this number here. So it's going to be the square root of a, which is -1/2 all squared, and our b here is √3/2, which we've got to square as well. So we end up with half squared, which -1/2 squared, which is +1/4, and then we've got to square this fraction here. Square the √3, you get 3. Square the 2, you get 4. So what we end up here with is the square root of 3/4 plus 1/4. So that's 4/4 or just 1. So what we end up with here is the square root of 1, which is just 1. So that's handy. So now we can just write down our complex number in polar form. So our complex number then in polar form, our original complex number was -1/2 plus √3/2. Remember, we want to raise this to the power of 3. So we'll just write it in polar form. So our polar form is going to be or, which is 1, and we want cos theta. Well, our theta is 2 pi/3 plus I sine 2 pi/3, and let's see, how many brackets have I got here? Yeah, I need another bracket here, I think. And we want to raise all that to the power of 3. So how do we do that? Okay, so we got to raise this 1. We got to raise this 1 to the power of 3, so that's just going to be 1. So really we just end up with, if you like, cos 2 pi/3 plus I sine 2 pi/3. Really we're just raising this part here to the power of 3. And using de Moivre's theorem then, we can just bring that 3 down here in front of the angle. So I'm just going to take this, bring it down here, and we're going to take this and bring it in here as well. So what we end up with is cos, well, 3 times 2 pi/3 is just 3 times 2 pi, because the 3's will cancel, or you'll just get 1, plus I sine 2 pi as well. Now it says give your answer in its simplest form, so let's see what we get here. Well, cos of 2 pi is the same as the cos of 0, so the cos of 0 is 1, and I here, and we got the sine of 0, the sine of 2 pi is just going to be 0. So really we just end up with 1. So minus a half plus root 3 over 2 all to the power of 3 in its simplest form is just 1. Okay, so that's it for this question.